It's like an electronic signature. So
Yeah.
Exchange that. All right, you ready?
Let's do it.
All right, let's get this thing on the road. All right, we are here today for Joshua's thesis defense. Everybody in the department knows Joshua. He's been here for a few years and has impressed all of his instructors in the classes that he's taken and has been a great help around the department. He's been working on this. There was a previous version of work related to this that he started maybe 2 years ago. And it's gotten to the point where we put it all together in a thesis, and that's what he's going to tell us about today.
All right. All right. So again, my name is Joshua Krotz, and this is the construction and evaluation of a gold standard syntax for formal logic formulas and systems. So this is just today's agenda. So we're going to go through the introduction, just a brief overview of the work, then the related work, current literature, the methods. So what did we do? Discussion of future work. Why did we do it? And what can we do to improve upon it? And then finally, the conclusion, just what did we gain from all this? So let's just jump right in. So classical logic, that is zeroth order and first order predicate logic, is essential to many disciplines. So in particular, you see it all the time in computer science, math, and philosophy, just to name a few. So where do we see it? Well, we see it through Boolean logic. We see it in selection and iteration statements, so loops and conditionals. We also see it with electrical circuitry, with logic gates, so NAND gates, NOR gates, things like that. And it's also it's the basis for mathematical and philosophical proofs. And the thing is, you use it almost every day without even realizing it. So take the statement, all computer scientists are good programmers. Now that's debatable, but you can represent that with first order logic. And the nice thing about it is that it develops good critical thinking and analysis skills in today's world, where you can easily see valid, invalid arguments and sound and unsound arguments essentially everywhere you go. So being able to go through that and analyze what makes an argument valid is very helpful outside of the mathematical components. So the thing with logic is that practice makes perfect, although you could apply this to any subject. And where do you get this practice? Well, you get it through textbook problems, you get it through exams, videos, lectures, things like that. Problem though, what happens when that's not enough? Perhaps the textbook problems just don't give the student everything that they need to succeed. That's entirely possible. One of those solutions comes through intelligent tutoring systems and calculators. So what do we mean by calculators? Well, you have things like truth table and truth tree generators. You have proof solvers, natural deduction calculators. They're all over the internet. You can find them essentially everywhere you go. So the nice thing about them is that they often give you independent instruction. They can be adapted for a particular student. And you have automatic problem generation, which means that if there's a problem, like if there's a certain aspect of formal logic that you're confused about, you can get problems tailored to that specific subject and work on that, which is something that textbook problems may not always have. The problem, though, is that there's a lot of variability in what makes a tutor good versus one that's bad. There's implicit prerequisites in that you often have to know how to use them in order to use them. So they're often, and that sort of leads into the fact that they can confuse beginner students more than they help. So if a student goes to one, they try to use it, they could leave not only not understanding what they're trying to solve, but also just they could be very confused by the tool. So there's that. So what did we want to solve? Well, we wanted to solve three big questions. So can we create a better classical logic tutoring system? So like I said, there are plenty out there, but we wanted to know if there's one, if we can improve on the current state of the art. 2, how can we compare natural deduction systems? So if you have multiple natural deduction systems, what makes one better than another? There's no well-defined metric for natural deduction systems. So we wanted to see if we could come up with one. And thirdly, a lot of math subfields have standardized syntax. So take set theory, for instance. If you see one book on set theory, it's most likely going to have the exact same syntax as another book on set theory. Formal logic doesn't have that same treatment. So we wanted to see if it were possible to standardize logic syntax. All right, so a brief overview of what we did. We created FLAT, the formal logic aiding tutor. We also created ANTAP, the automatic natural deduction tutor improver. FLAT is a desktop application, ANTAP is a web application. We compared 4 publicly available natural deduction systems. And lastly, we created a gold standard syntax for both 0th and 1st order logics. All right, so that's the brief overview. Now we're going to jump right into the related work. So the thing about tutoring systems is that they're not new, but over the years, they've gotten progressively more intelligent. But what does it mean to be intelligent in this context? It's the ability to create a good relationship, or it's the ability to mimic a relationship between a teacher and a student. Okay, so taking a step back, we have the truth table and truth tree generators. So they're all over the place. And like I said, they often require prerequisite knowledge of actually using them. And another problem is that they often serve as a solution provider and not a tutor. So you input a formula, you get a solution. What do you take away from that? Usually not a whole lot. So a good example of an intelligent tutor is the P-Logic tutor, developed by a group of researchers at Wake Forest. And they evaluated it with a few discrete math courses. And it has some nice built-in functionality, so truth table, truth tree generators, natural deduction tutoring system. But we can't evaluate it today because it's offline. And if you even wanted to use it, you had to have an account with Wake Forest, so it wasn't publicly available. So at NC State, there's a project called Deep Thought, and it's a data-driven project for generating dynamic problems and dynamic hints. So if a student is struggling with something in particular, the system can generate hints for that particular problem or that particular concept. And the same goes for problems. And there's also the APROS proof generator for the Open Learning Initiative project at Carnegie Mellon. Though the problem with both Deep Thought and APROS, similar to P-Logic, is that there's not a whole lot of modern research on this. These are probably around 10 years old, I'd say. So we can't evaluate them today. Especially APROS. I was very surprised that there's really no reference to getting their system now. Okay. So another interesting tool, and when I say interesting, it's interesting because it's an Android application. So everything we've seen thus far is either a desktop or a web application. But Axolotl is a first order proof and type theory application. So it's for more advanced students, but we put it in there because it does have a fixed style natural deduction proving system. And on a different note, or a related note, there is False and Logic Chess, which are graphical applications that let you learn first order logic. So let's just take logic chess, for instance. You're given a chessboard and you can use predicates to determine or define the state of the board. So you say, is below can be a predicate, and you can say the queen is below the rook, something like that. So it's a nice little graphical application. So the thing about these intelligent tutoring systems is that they have to have some type of theorem prover to actually solve the problems that it generates. That's just how it has to go. That's how you provide dynamic hints. So a historical example of a theorem proving programming language is Prolog. And to go along with that, Muggleton actually coined the term inductive logic programming. So Prolog, you give it a database of facts and rules, and then you can deduce other information about the facts and the rules. Inductive logic programming works a little bit backwards. So you give it the background knowledge and a hypothesis, and that can produce other rules from that. Okay. So I'm going to put these two together because they're fairly similar. So Coke and Isabel are functional programming proof assistants. So the keyword there is proof assistant. So they're not something that you can just input a formula and it will give you the result. It can, you can have that, but it's not entirely designed for that. But Coke is used in program verification, a lot of mathematical context, and Isabel tends to focus more on higher order logic. And there's actually a system called Nadia, so I'm going to pronounce it. It uses Isabel as a backend to actually generate and verify natural deduction proofs. So Isabel doesn't do it by default, but it can be used for that. And importantly, there are many, many, many others, as we referenced here, but a lot of them sort of branch out into different subsets of math and computer science. So we're going to omit their discussion. All right, so jumping into standardized syntax. So the ISO, the International Organization of Standards, they actually do have a section for logic or logic symbols. The problem though is that while those symbols are used in some contexts, it's not widely recognized as a standard. And to sort of go along with that, there's really only been one attempt at actually trying to give syntactic meaning to certain symbols. And it was by this researcher for his calculus classes. So what he did was he uses these bold left, right, and right arrows for statements that are always true. And he uses these thinner arrows, thinner right and left, right arrows for claims that can be either true or false. So it helps distinguish what is a theorem and what can be proven, so to speak. And he also prefers parentheses and brackets instead of the default operator precedence, which that's a sentiment we also share. But other than that, there's no real attempt to give there's no attempt to standardize logic syntax. Okay, so lastly, we're going to talk about SAT solvers. So SAT is one of the most fundamental problems in all of computer science. And the basis of it is that it has no known efficient solution, but it's very important for certain applications. So with that, there are approximation and heuristic algorithms. So, and those are some of the examples right there of different SAT solvers. But why is that relevant? Well, there are things called SAT competitions where people can enter their system and it will be evaluated on different formulas to try and solve them. But the important thing is that they use this format called the DIMAX format. So every system has to adopt this standard in order for it to be testable. And that's something that we wanted to try and experiment with when testing natural deduction systems. All right, so now let's jump into what we did. So we did two experiments. So the first one is a student-driven approach. We wanted to answer the question, what makes one proof or formula harder than another? Because sometimes it's not readily apparent. And the important thing is that what one student thinks is difficult, another student may not think is difficult, or vice versa. And importantly, an expert who may think one thing is hard, that may not always align with what students think is hard. So the idea, why don't we just ask the students what they think is hard? So that's what we did. So we created 2 surveys and a study. Well, it's all one study, but 3 parts to it. So the first is a premise and conclusion interpretation survey. Second is a natural deduction proof interpretation survey. And the third is they actually had to solve natural deduction proofs with our system and TAP. So here's an example of the first two surveys. So this top part here is an example of a question that we would give them. So they would be given those two pairs of premises and conclusions, and they would have to, just by looking at it, determine or think which one looks harder to prove. There's no right or wrong answer. It's just to see what they think personally. And the same goes for the natural deduction interpretation. So they'd be given a proof, or two proofs rather, where they prove the same conclusion, but they may be given slightly different premises. But ultimately they reach the same conclusion, but there could be different rules applied. So as we can see on the left here, there's a motorist tolerance rule, and on the right, there's a disjunctive syllogism. But they both reach the same conclusion, and they just have to say which one looks harder to understand. All right, so now we're going to show what they had to do in ANTAP. So this is ANTAP. There are three components, so we're just going to go into the observational study portion. Just put in anything for the email. So this is what they got. So there are 10 proofs that they had to solve, and they could go between them like this, and they were given the conclusion. So this is the one that I actually showed on the screen. And they would try to solve the proof. So for instance, we could apply a conjunction elimination rule and then submit it. And they would just keep going until they derive that conclusion. Okay, so in the study, we would record how long it took them to solve the proof, what steps they took, if they got it wrong, if they were able to solve it at all, things like that. Okay, and it also tells you whether you've applied a rule incorrectly. So if let's just say we use two rules or two formulas to use a conjunction elimination, it will say that there's an invalid rule because you only need one line for that particular rule. All right. So what did we want to find from these three components though? We wanted to know what the common mistakes were and what patterns we could observe from this to find or sort of deduce what is difficult to a student. However, we noticed that even with pretty heavy recruiting, we just didn't get that many participants. So we had 2 that participated in the surveys and none that actually participated in the ANTAP portion. So we don't have any definitive results or any definitive conclusions, but we will still mention what we found among those 2 participants because it is still important to see. All right, experiment 2. So this experiment was about determining what makes one natural deduction system better than another. First problem though is actually finding these systems. So unlike truth tables and truth tree solvers, those are everywhere, but natural deduction systems are actually pretty closed off. You'll find a lot that are in research groups, but you can't access them just because they're either closed source, and by closed source, I mean, not only can you not access the source code, you also just can't use them. A lot of them are dead projects, so they've been dead for many years, or we just somehow can't access them. And second, what does it mean for a system to be successful? So without student interventions, it's pretty difficult to define. So we used the metric of success being short and concise proofs that students can understand. So short proofs that make sense to a student, because if proof is very long and unwieldy, they're not going to want to understand it, or they're not even going to try to understand it, most likely. So the 4 systems we tested are Flat, which is our system, a website called Teaching Logic, a Windows 10 application, Natural Deduction, and another website called Taught Logic. So what did we collect? Well, we collected the number of lines in each proof, and we'll give a little bit more information about the actual proofs in a minute. We also collected the number of axioms for a particular proof from, like, if a system had 6 rules in its base set of axioms and it used 3, we would record that. and also whether or not it actually succeeded. So whether it was able to solve the proof or not. All right, so now we're going to actually demo these 4 systems. So first, let's demo flat. So this is flat. There's a lot of neat tools in here, but the one that we're going to care about is the natural deduction component. So let's just enter a simple proof. So we'll do C or not D, not C, A implies D, therefore not A. So this is pretty simple to solve. So as we can see, it actually solves it with only 2 rules, which is pretty nice. But in addition to the solving component, there is a practice mode as well. So if we just turn on the practice mode over here, it will change to this and give a little bit of information on the right side here. And the students can enter a formula. They can enter the step, which is just the rule that they want to add, and also which lines contribute to that step in the proof. So it's very similar to ANTAP. All right. So now let's go back to, this is teaching logic. So immediately, what is nice about this is that it's a web application, but the problem is its input syntax. So everything has to be conjoined as a series of conjunctions, which imply the conclusion. So let's format that same proof that we had with this syntax. So we'll do, let's see, C or not D, then and not C, and A, then D, therefore not A. Okay, and then it gives the proof. So it can annotate the proof with these steps right here. So we immediately see that there are a lot more rules with this particular system that are applied because it uses nested proofs, and proofs by contradiction, which can be a little bit unwieldy, especially if you don't understand how indirect proofs work. So that's that system. So now let's switch over to the Windows 10 application. So this is natural deduction. That's just what the name of it is. And this system is, well, we'll go over the results of what we found at the end of the discussion. So let's just go ahead and do the same proof and see what we get. So C or not D, C not C, A then D, and therefore not A. And this one has 27 steps. So we'll come back to this particular application in a minute because we observed very unwieldy proofs with this particular system. Not entirely sure why. It was very inconsistent. All right. So now let's go. No, let's not do that. There we go. All right, and this is taught logic. So this was the only system that we tested that actually had both propositional and predicate logic support. So, and another thing is that we have to use these atoms here. We can't use A, B, C, D, and so on, which is an odd restriction, but we'll do that. So let's do R or not S, not R, P then Q, or P then S, therefore not P. And it shows the proof, and you can do it yourself, or you can solve it. So one immediate thing that we noticed is that almost all these systems do proofs by contradiction or do indirect proofs when they really don't need to. So let's jump back into the presentation. So what did we learn? Well, as you may have noticed, each system has its own syntax requirement. Each one has certain symbols that it can use and understand. But we also noticed when we were testing it, that flat generates shorter proofs more consistently, proofs that students can understand and digest. And importantly, it's very difficult, or it's very cumbersome. It's not difficult, it's cumbersome to test systems very quickly. So we created 288 proofs. And with 4 different systems for syntax, that's over 1,100 proofs. And if you want to test more systems, just multiply that number by n+1. So it gets pretty ridiculous. So that actually inspired the desire for a gold standard syntax. So we're going to jump right into that now. So with this is just propositional logic, and there are many symbols that can represent the same semantic idea. And here's just some of them. There may be even more. And even more important is that, as we saw, atoms, predicates, constants, variables, they can all use different letters of the alphabet, different cases, and it gets very unwieldy to use, especially if you're trying to test systems very quickly. So what do we want to do? Well, we wanted to create a way to go from one logic language, which we define as L, to this gold standard, which we'll define on the next slide, to another system, which we'll just call, or another language, which we'll call L prime. So we'll just put it all up there at once. So this is a little bit esoteric notation. That's fine though. The idea here is we want to create a function that will take in one logic language, which this is just for 0th order logic, so propositional logic. You only have connectives and you have atoms, so you don't need a whole lot to go from one language to another. We define constants by this function, or atoms, not constants, by this function zeta. And the connectives are mapped using the function delta. So connectives in the gold standard use these uppercase letters right here. So instead of having to use some symbol like the plus sign, the wedge, or anything for a connective, we just use uppercase letters. So that makes it pretty simple. So it's interesting to see this as an example, so we're just going to jump right into that. So, but first off, the advantages of the gold standard are it's easy to define, you can reverse it easily, it's parsable, so you can write a system that will interpret it fairly easily, and it also allows for unambiguous formulas, so formulas that are unambiguous in terms of precedence and associativity. So here's an example. So let's take this formula, the biconditional, just a couple clauses, and we'll convert it into the gold standard. So we define these two functions, delta and zeta. So we just say that each connective in this language maps to these symbols. And then the atoms, we're just saying that this language supports the uppercase letters P to Z for atoms. So those map to A subscript 1 to A subscript 11. And it converts into this prefix notation. So that's what makes it unambiguous. And it may not be as easy to read as something like this, but we can read it left to right. So this reads as a biconditional of two formulas, where the left is a negation of a disjunction, and so on and so on. So it's very easy to semantically understand. It may not be as pleasing to the eye, but you can read it and understand what it's trying to say. So just like for 0th order logic, we did this for 1st order logic. So the only difference here is that we need 3 new connectives. We have the 2 quantifiers and the identity operator. So we just said those were Z, X, and V for the universal, existential, and identity operators respectively. And instead of atoms, we have 3 new functions, sigma, chi, and eta, where each one is either the predicate mapping function, the constant mapping function, or the variable mapping function. So again, we'll just show this as an example. That's the best way to do it. So we're going to convert this formula, very complex formula, into the gold standard. So again, we just define delta, same function as before. Let's see, then we define sigma as the predicate mapping function. We define chi as the constant mapping function. We're just saying in this language that constants are lowercase letters a to t. And eta is the function, or maps u to z, lowercase, as variables, and we get this prefix notation. So if you've ever programmed in Scheme, this will look familiar, but this is also just standard prefix notation that you could see with standard mathematics. All right, now we define this for zeroth and first order logics. That's great and all, but the whole idea behind this was to define it for natural deduction. So what about that? Well, we can define that pretty easily. So we just create this new function n, which takes on a list of premises and a conclusion, and we can define it like this. So let's say, this is the exact proof that I've been showing on the systems. We're getting a list of premises and a conclusion, and we can just convert that into the gold standard. So we use the same functions, delta and zeta. It's fine. And this reads as hence, so therefore not A1 if this premise is true and this premise is true and this premise is true. So it's almost identical to Prolog syntax. Okay, so we don't need to redefine anything for zeroth or first order natural deduction because it will just use it by default. So if you have a proof that's in first order logic, it will just take that standard and use it, which is pretty nice. All right, well, now we've discussed our methods. Let's go into actual discussion of the results and what we can do in the future. So as we said, experiment 1 was pretty unsuccessful just because we didn't get that many people, sadly. But we will mention the themes that we saw from those 2 results. And just as we sort of suspected, larger proofs were seen as more difficult. That was expected. Something else that was expected was that proofs with a bunch of negations and disjunctions were viewed as harder than ones with just implications. And lastly, there were rules like that use distributed properties. So something like De Morgan's. These just come down to preference as to what they think is difficult. So we can't really say anything definitive about that. But what's interesting about this is that if we know what makes a formula difficult, if we know what makes logic difficult, so to speak, in this context, we can improve the teaching of it. So if students struggle, if the majority of students struggle with one particular thing, we can emphasize that when teaching it or create more exercises based around it. So future work for this, create better surveys, do more recruiting, make it a part of an actual course. And that's what we saw with the related work. A lot of tools were used and integrated into courses. So that requirement allows or mandates that students do it. So you get obvious results. Okay. So now experiment 2. So as we said, flat generates proofs that were shorter overall out of those 288 proofs that were simple using our metric to understand versus the other 3 systems that we tested. We also saw, as we said, that other systems were just generally unintuitive and they require different input syntaxes. So students will often have to learn how to use the system. So for someone like me who has learned the systems to do research with them, it's pretty quick. But imagine a student who is learning it to learn the material, they could get overwhelmed very quickly. So one example of that is just in teaching logic, where you have to use it as a series of conjunctions. So students may not have seen that before and just expect something different. Okay, so going back to that Windows 10 application, natural deduction, we saw that some of the proofs with that system generated proofs that were 250 lines long for seemingly no reason. Sometimes the proofs would be very simple, and sometimes they would be completely wild and just unmanageable for no discernible reason. We just weren't sure why that was. It could be just related to the algorithm they used. We're not entirely sure. In taught logic, they had a lower percentage of success. And also one thing that we noticed, which was kind of odd, was that you can't use general operate or widely used connectives like the wedge or the plus sign for disjunction. You have to use the words or, implies, or then. And that's kind of odd that you have to do that. But that's what you have to do. So future work. So we want to continue improving flats and ANTAPS algorithms. So make them succeed more, increase their success rate, and also make them more pedagogically appealing. So right now they sort of serve, they do have the tutoring aspect, but we would like to take inspiration from projects like Deep Thought to generate dynamic hints, dynamic problems. So that's something that we would like to do in the future. And also, so jumping into the gold standard, just because we define a gold standard, that doesn't mean that people are going to use it. Everyone has their preference as to what they think is right and what is wrong, and we are no different. So in order to standardize this, we would have to have participation from the community. But recall our focus here. We want to be able to create some type of syntax where you can compare systems quickly. We want to be able to evaluate the systems for their performance and their efficacy. So what can we do to improve that? Well, we can either create software to do it automatically. So if you specify the delta and zeta functions, it will convert to the gold standard or vice versa. Or we could write our own programming language for that. And also we want to compare and evaluate other systems that are out there. So look harder, see if there are any that are open source in the broader research community and things like that. So in essence, intelligent tutoring systems are really, as the slide says, very important. Some, as we saw, some have their pros, some have their cons. It just depends on where you look. But as a broad goal, we really want to make flat and ANTAP better because, like I said, right now they're very nice, and flat is more powerful than ANTAP in the sense that it has more features. We would like to fully convert that into a web application since it's easier to use like that. And going back to this gold standard idea, we want to standardize, we should standardize logic syntax. So that's going to take time. It's going to take more research, more experimentation with other systems to see how well it works. And lastly, it's difficult to define difficulty metrics. So as we said, what makes one system or what makes one formula harder to a student will be different depending on the student, depending on what major they are, depending on how much background they have. So more studies, more work will have to go into what makes something difficult, what makes a formula difficult. And that's it. So, questions?